In the middle of the Pacific, a steel hull cuts through the waves under a full moon. On board, silence dominates, broken only by the hum of a cryogenic compressor cycling between 1.3 and 1.0 C. Inside a sealed chamber, dozens of swordfish lie arranged like aircraft components, each wrapped in a layer of thermal gel, each monitored by independent sensors. This isn't a fishing boat. It's a floating cold chain lab. Because shipping swordfish is not about volume, it's about precision. It's about keeping a biological structure, fragile at the molecular level, intact across oceans, climates, and borders. Swordfish are more than fish. They're metabolic puzzles. Unlike grains or frozen peas, their muscle fibers degrade in curved decay patterns. A variation of just 1.5 C above the ideal storage temperature of 1.1 C can double the rate of tissue deterioration. And that curve is exponential. What begins as a barely noticeable deviation in the hold becomes, 36 hours later, a breakdown in cell membranes and a rise in histamine levels that no visual inspection can detect. That's why the threshold isn't set casually. It's measured in half degrees. The logistics behind this aren't about getting a cold box from A to B. They're about designing mobile ecosystems where temperature behaves like a constant. To understand how critical this is, imagine the same principles used in nuclear submarines. Deep under the Arctic shelf, crews spend months submerged, with no resupply and no margin for spoilage. Their food systems rely on zoned refrigeration, where different sections preserve food at tailored conditions based on moisture, density, and storage life. The swordfish container works the same way. But instead of feeding a crew of 120, it supplies high-end markets across Tokyo, Dubai, and New York, where a single kilogram of fish can reach $70 retail. If the cooling isn't zoned, if the airflow isn't uniform, if the packaging absorbs ambient heat even briefly, the value of the shipment collapses before the plane even lands. This is why swordfish logistics resemble mechanical surgery. Every part of the chain, catch, pre-cooling, packaging, storage, transport, must behave like a synchronized actuator, like the nozzles of a self-propelled sprayer adjusting micron-level droplets over hectares of soybeans. The cooling systems in swordfish freight respond to micro-fluctuations in cabin air pressure and external humidity. They adapt, adjust, and self-correct, because unlike most cargo, fish don't just expire. They evolve toward failure if not managed thermally. Each journey begins with a choice. Treat the swordfish like a bulk product and lose 20% to spoilage, or treat it like an organ for transplant, where every tenth of a degree is monitored, logged, and accounted for. In this world, temperature is not a condition. It's a command protocol. Welcome to the hidden symphony of marine cryogenics and cargo engineering, where time, biology, and refrigeration form a single, silent choreography. The first few hours after a swordfish is caught are decisive. Not symbolic, not operational. Decisive. Because during that brief interval, muscle tissue, still metabolically active, begins to collapse inward. From the outside, nothing changes. The skin remains intact. The color holds. But internally, the biochemical clock has already started ticking. And the longer the fish waits before pre-cooling, the faster that clock counts down. What's lost is invisible. Protein integrity, moisture retention, and most dangerously, histamine levels that spiral beyond safe thresholds with no warning. These are not flaws you can see at the dock. They emerge days later, thousands of kilometers away, when a receiving lab rejects a batch because the degradation happened before the cold chain even began. To close that gap, technology has moved closer to the source. On some long-line vessels and landing piers, mobile vacuum cooling stations have been installed. These are not refrigerators. They are pressure-controlled chambers where water evaporates rapidly from the fish's surface, pulling heat with it in a process more efficient than ice. Within just 45 minutes, the swordfish's core temperature drops below critical levels, locking in freshness before degradation accelerates. Unlike ice, which cools slowly and unevenly, vacuum systems remove heat from the inside out, sealing the fish in a metabolic pause. What used to take hours now takes minutes. And in this trade, minutes define market access. The difference is measurable. In 2023, a comparative study across Chilean Pacific ports tracked swordfish from identical catches. Those pre-cooled with vacuum chambers retained 28% more protein integrity after 7 days in refrigerated transit than those handled with standard ice methods. That margin doesn't just influence flavor or color. It determines whether a shipment is accepted or incinerated, because major importers, especially in the EU and Japan, have tightened histamine tolerance to thresholds as low as 100 parts per million, and enforcement doesn't wait for suspicion. It's routine. The consequences are already on record. In May 2021, a high-value export batch from northern Peru arrived in Rotterdam. It had passed visual inspection at departure. The packaging was sealed, but when random units were tested at the European port, histamine levels exceeded legal limits by 11 ppm. The cause? A 6-hour delay between docking and the start of cooling, caused by congestion at a regional landing site. That delay, unnoticed by the crew, triggered a loss of over €140,000 and a cancelled contract, all because the fish waited, in open air, under 26 degrees, for too long. This raises an uncomfortable question. If 4 hours of uncontrolled time can undo weeks of planning and thousands of kilometers of precision transport, how robust is the average post-harvest calendar? How accurate are the real timelines, not the ideal ones, between catch and chill, load and move? The answer lies not in more refrigeration, but in rethinking the start point, because the cold chain doesn't begin at the container terminal. It begins the second the fish leaves the sea, and the system either captures that moment or lets it slip irreversibly. At first glance, a fully iced container packed with swordfish appears secure. The cold is visible, tactile, even theatrical. But inside that apparent uniformity hides a dangerous imbalance. Because ice in bulk behaves like a static blanket. It cools by contact. It melts unevenly. And it cannot respond to airflow dynamics or packaging geometry. The result is thermal stratification, zones where the fish remain too warm for too long, surrounded by other areas that are over-chilled and structurally damaged. The core of the container may stay insulated for hours, while edges suffer heat ingress from ambient exposure, contact loss, or air leaks around poorly sealed doors. This is not a minor variation. It's a structural flaw in traditional fish logistics. And it's why, increasingly, exporters are replacing crushed ice with eutectic plates and phase-change gel blocks arranged in vertical modules. These systems don't just cool, they shape how cold moves. By placing the cooling sources around the product in defined arrays, they create directional thermal flow, ensuring that each swordfish is enveloped in a uniform thermal field rather than buried beneath melting ice. The change isn't about aesthetics, it's about physics. Because consistent cold is not about temperature, it's about distribution. Nowhere has this shift been more rigorously tested than in Japan's premium tuna exports. There, directional eutectic systems have replaced ice in high-value shipping, with studies showing a 73% reduction in core temperature variability compared to standard ice packing methods. The fish arrive not just colder, but equally cold, center to edge, top to base. That consistency doesn't just preserve freshness. It eliminates the risk of micro pockets where spoilage can begin unnoticed. It transforms each container into a controlled environment, not a passive vessel. In Brazil, this strategy has been adopted for outbound shipments to Hong Kong, where shelf life demands are strict and inspection layers are deep. Exporters using modular eutectic pallets reported an increase of 22% in product longevity, with direct consequences: longer shelf presence, fewer losses, and the renewal of purchasing contracts at higher unit prices. In the competitive fish market, that margin determines whether a producer stays in the premium category or falls into commodity-grade anonymity. The difference is not volume, it's control. So the issue is not whether the cargo is cold, but whether the cold is in the right shape, whether it reaches each kilogram of fish evenly, predictably, and sustainably. A block of ice can freeze a surface, but if the air around the fish is unstable, if the thermodynamics inside the container fluctuate across zones, then cold becomes a liability, an illusion of safety masking internal failure. And in a trade where reputations are measured in repeatability, The shape of the cold matters as much as the number on the thermometer. A container is not just a container, not when it carries swordfish. What looks like an ordinary steel box rolling down a highway or gliding into a port is, in truth, a mobile climate system, calibrated down to the decimal to preserve the most fragile version of protein that international trade can offer. Every detail, temperature, airflow, packaging shape, internal humidity, is pre-engineered not to store, but to preserve, not to cool harder, but to cool smarter. Swordfish doesn't travel like bulk corn or boxed soy. It travels like a compound, like a structure designed to remain molecularly stable under precise thermal conditions, despite time, turbulence, and transit. This is what turns swordfish shipping into food engineering. Because at this scale, quality isn't maintained by chance. It's sustained by design logic. Just as a combine harvester doesn't simply gather crops but performs a simultaneous choreography of cutting, separating, calibrating, and data logging at each meter it travels, swordfish transport executes a multi-layered sequence: internal heat extraction, zoned refrigeration, kinetic insulation, humidity balance, and adaptive airflow, all while moving between ocean, road, airspace, and distribution centers. The process is invisible, but it is constant. We often imagine logistics as the end of the journey. A fish is caught, processed, and then it's moved. But in reality, logistics is the second phase of a live operation. It doesn't begin when the doors close on a truck. It begins the moment the fish is removed from the water. The thermal timeline starts then. Swordfish tissue continues to metabolize for several minutes after death. Enzymatic reactions begin altering the protein bonds almost immediately. That means the first 2 hours are not just operational, they're biological. And if cooling isn't applied within that critical window, the rest of the chain becomes a compensation effort. At best, it slows degradation. It cannot reverse it. This is why modern cold chain systems have evolved beyond simple refrigeration. In high-value seafood routes between Ecuador and Korea, Brazil and the UAE, companies like Maersk deploy smart reefer containers equipped with microclimate zoning. These are not traditional reefers with a single airstream. Instead, they contain multiple temperature zones controlled independently by algorithms that process both internal sensor data and external climate forecasts. A shipment with different cuts, whole fish, loins, skin on fillets, can be placed in different modules within the same container, each one responding to the specific thermal needs of that format. The system doesn't just react to temperature, it anticipates it. The technological parallel to precision agriculture is not coincidental. Just as an intelligent seeder adjusts seeding density and depth based on real-time soil moisture readings, these containers adjust compressor load, fan speed, and vent cycling based on predicted thermal loads at upcoming altitudes and ambient temperatures. In both cases, success is not measured in averages, it's measured in consistency. A perfectly calibrated field delivers uniform emergence. A perfectly cooled container delivers uniform protein integrity. One mistake doesn't just impact one point, it cascades across the system. This isn't abstract. It affects how long the product lasts on a shelf, how it performs under inspection, and how much buyers are willing to pay. In the global seafood market, shelf life isn't just a biological measure, it's a financial instrument. An additional 2 days of optimal condition can mean access to a different tier of restaurants, export categories, or air freight routes. And that shift, driven by better cooling design, transforms the economics of the entire operation. But beyond the financial layer lies something deeper, a philosophical elegance in the orchestration of cold, time, and biology. A discipline where engineers, biologists, and logisticians work not just to move something from one side of the world to the other, but to preserve its identity along the way. In this chain, the fish is not just cargo. It is the product of a choreography involving hundreds of variables, each measured, tracked, and corrected in real time. This is not storage, this is conservation, and the margin for error is as thin as a thermometer probe. So when a swordfish steak arrives on a plate, pink, intact, glistening under lemon and oil, what you see is the final frame of a silent movie that played out across thousands of kilometers. A movie where every sensor, every refrigeration cycle, Every airflow duct performed a role. Behind that flavor lies mechanical intelligence, thermal choreography, and a chain of decisions timed to the hour and measured in microns. The cold chain is not just part of agribusiness. It is its most precise, invisible engineering. And when it works, it makes the impossible, moving life across oceans quietly routine.